Hello, guys. Welcome back to Maison African Motives. Still working on engineering science N3. In this case, working on motion, energy, and power from the question paper of November 2019. So we are given the first part of the question to name one difference and one similarity between speed and velocity. Okay, what is it that we have between these two? The speed and velocity, but the first thing is supposed to be on the difference and the similarity in this case. Okay, so remember that if you are referring to speed and velocity, these two, they are actually sharing the same thing, which is the units of measurement. These two are measured in meters per second. So these two here, they are measured in meters per second, which is the similarity in this case. So we've got a similarity that these two, they are measured in meters per second. So measured so you can just say both, okay? Both measured in meters per second. But on the difference, how can we differentiate between speed and velocity? Okay, so the difference is that the speed is referred to as a scalar, and a velocity now is referred to as a vector. So we are referring to a scalar and velocity, a vector quantity in this case. So this is the difference that we are going to have between these two. All right, if we check on 1.2, we are given that a BMW car is with a mass of 1.2 ton, accelerates uniformly from rest up a gradient of 1 in 20 and reaches a speed of 15.5 meters per second after 3 minutes. So take note, this started uniformly from rest, but it's on an incline. That is what we are given in this case. So this is on an incline. So that's 1.2. So that's something like this. On an incline, all right, where we know this is going to be 90 and we've got our angle theta. So our object started at rest at 0, going up of the incline, okay? So what we need in this case, let us just take our information so that we'll see what we are given. So we are given the mass of the car of 1.2 ton. Remember, the ton represents 1,000 kgs. So we've got the mass there, which is, we can write this in kgs. So the mass of 1.2 ton is equivalent to 1,200. That is 1 ton is equal to 1,000 kgs. So you multiply by 1,000. So this will be 1,200 kgs or kilograms. Okay, but we are given that this started from rest. So from rest, that is our initial velocity, that at 0. And we are given a gradient of 1 in 20 up, it reaches a speed of 15 meters per second, which is the final velocity. So we've got from rest up to the final velocity of 15 meters per second. All right. So when we are saying from rest, that means there is no movement at all at rest. So our speed is at 0 meters per second. Then we've got the final velocity now, which was at 15.5 meters per second, but we are given a gradient of 1 in 20. So given a gradient of 1 in 20 means 1 over 20. That is from arctan, we can obtain theta from there, from the gradient. So arctan of this 1 over 20, which is going to give us something like 2.862 and so forth. But actually remember what I said, guys, that if you are given the tan of theta, this is actually a small angle, 2 degrees. It's actually a small angle that you're talking about. So on such conditions, we can actually also use the approximation that the sine of theta approximates to the tan of theta. If theta is small, so we can actually use the sine theta in place of the tan, which is actually fine, but you can also apply this angle as it is. It's one and the same thing. We shall see that in our calculations. Then we are also given the other part of the information is the time frame between this movement from rest up to the final speed. It was in 3 minutes. So we are supposed to have our time in seconds. All right, so we are going to have our time 3 minutes convert to seconds. So that will be 3 minutes in seconds. That is, you multiply by 60. Remember, 1 minute is 60 seconds. So this will be 180 seconds. So for the time. Okay, so this is the whole information that you're given. From there, we are given to calculate the acceleration of the BMW. That is the acceleration of the car. Take note, we are told that it started from rest up to it reaches a speed of 15 meters per second in the time of 108. So we can actually formulate the acceleration from there, from our linear motion that we have, or from the linear laws that we've got. Remember that V is equivalent to U plus 80. We've got a lot of formulas that we have got there. Also, where there's acceleration, remember that V squared is equal to U squared plus 2AS. We also have S, which is equal to AT, that is going to be UT plus half AT squared. So we've got a lot of formulas that we can use, but which one of these formulas can we use according to the information that we have here? So if you are to see, the best formula that we can apply is this one, because we've got the final velocity, the initial. We also have the time. All we need is to find A, which is the acceleration. So you can use this formula. Okay, so on 1.21, using the formula V is equal to U plus AT, we can make A the subject, or we can substitute our values. If we make A the subject, U to this side, it is going to be V minus U, which is equal to AT. Remember, we want to calculate A, so you can divide by T both sides. So that's here. The acceleration is equal to the final velocity minus the initial over the time that you're given. So we can substitute our values there. That is V, the final velocity of 15,5 minus the initial velocity. That's 0 over the time that was taken in seconds. So our time is 180 seconds. So this is going to give us the acceleration of the BMW in this case. If you substitute your values properly, you're going to obtain something like 0.086111 and so on. So to 3 decimal places, this is going to be 0.086. Remember, acceleration measured in meters per square second, or you can write as meters per square second in this format. Okay, any way of writing it, still one and the same thing. So this is what we obtained from the formula that we are given, and the information. So take note, the other formulas we can't use. The first one, we do not have the distance. S is for the distance. This still applies. With the second one, we can't use it because we do not have that. We do not have the S, but we can find that the displacement or the distance. Then we can use it to calculate acceleration, but it will be a lot of time that you are using there. All right. If you take note about the other part of the question, which is on 1.2. We are now given to calculate the kinetic energy the BMW possesses after 3 minutes, which means within this same time that we have been talking about in the 3 minutes, where we calculated the acceleration in the same 3 minutes. What about the kinetic energy? All right, so how do we calculate? What is the formula actually for kinetic energy? Remember that kinetic energy can be obtained from half mv squared. You're also given this on our formula sheet. So this is the kinetic energy is equivalent to half mv squared. Half times the mass times the velocity, which we have got the mass and we've got the final velocity. So here we can just easily substitute our values. So that is going to be half times the mass, which is 1,200 in kgs. So we've got 1,200 times the velocity in meters per second, which is 15, the final velocity that you're given, that is 15,5. So you're going to have 15,5 squared. This is V squared. So this is going to be squared. All right. So this is going to give us the kinetic energy in this case, which is going to be 144. So that is going to be 150 joules in this case, of which you can convert to kilojoules. So that's in kilojoules. You can have this as so you can just even convert to divide by 1000. So this will be 144,150, of which the zero does not matter. So you can even convert your answer to kilojoules if you want. We are not told about the units. It's just to calculate the kinetic energy. All right. So let's check the other part of the question. On 1.23, we have got the gain in potential energy. What would be the gain in potential energy? Okay, which is one of the major parts that you are supposed to consider here. Remember that if we are talking about the gain in potential energy, what we need is to have the height. Okay, let's have our formula above so that I just use this diagram here. If you note that our potential energy is supposed to be taken from this formula, that is potential energy is going to be mgh. But because of the incline that we have got here, this is going to be affected. The h that we are talking, this is our h that we are referring to. So this h is going to be taken from the angle that we have got of theta, which I said before, instead of using this theta, still you can just use the sine theta as it is, okay? So remember that here we are supposed to have the h from the distance, which is our display from this point up to this point. So here we are going to have the distance that we are going to refer to as s. And from our Pythagoras theorem, from our trigonometrical ratios concept, from the sine of theta, this is going to be h sine the h is going to be s sine of theta. Okay, let me just write this formula so that you understand where it is coming from. Remember, the sine of theta gives opposite over the hypotenuse. That is, the sine of theta is equal to the opposite, which is our h in this case, over the hypotenuse, which is the longer side, opposite to the 90 degrees, which is our s. So we can actually find h by cross multiplying 1 times h, that is h is equal to s sine of theta. So in place of this h that we are having, we are supposed to have this as s sine of theta. That is the concept that you are referring to in this case. Okay, so if we are to consider this here, that means we can just rewrite our potential energy as mg times the h, which is representing s sine of theta, which is the displacement s. So we need to calculate that. Which formula that you can use to calculate? Remember, I listed the formula before. If you are to consider whether you're going to use the first formula, this one, you can calculate s from this one, or you can make s the subject from this formula here, because we have got everything in this case. If you are to take note, we've got everything. Also, we have got this formula to calculate s, which is given as u plus v over 2 times the time. I've also talked about this formula before, which is the best formula because if you consider this formula, u and v were the original values that were given before, which means we are using original values, and also the time. So which means we are obtaining exact values. If you use this formula, it is going to affect us, but it's fine because of our acceleration. We calculated acceleration, so it's a rounded figure value that we are using. So we are not going to obtain the exact answer that you're supposed to have, but still it's okay to use any of these formulas to calculate s. So I'm just going to take advantage of the first part here. This one is going to be the easiest for me, so I'm just going to use that one. So since s is equal to u plus v over 2, that is u, the initial velocity which we are given before our initial 0, v 15,5. So we are going to have 0 plus 15,5, that is our initial plus the final 0 plus 15,5 over 2 times the time frame that we are given. Remember, our time before that we had was 180 seconds, where we calculated here, where we substituted t is 180, the one that we sub from our information. Also, we are given this. All right, so this is 180. So this gives us something like 1,000. That would be 1,395 in meters. So like I said, You can use any other formula, but our answers, they are not going to be exactly the same, but we are in the same way. So if you are to take this S that we got here, so now we can just substitute, because remember, I calculated, okay, I stated about theta here, that theta is going to be arctan 1 over 20 in this case, which is going to be 2,862, or we can use the sine theta as it is, which is to use the 1 over 20 as it is. Okay, so let's substitute into our formula. The potential energy that we are having is going to be mg times s sine of theta. So we are going to have our EP as the mass. Remember, our mass was 1,200 kgs, times the gravitational acceleration that you are given as 9,8 from your formula sheet. So take the information that you're given. Sometimes they can give you 9,81. You use the one that you're given. So our mass here. So times S. Now this S here is the one that we calculated, which is 1395 times the sine of theta, which you can use, guys. Take note, you can actually use the angle because you have it 2,862 degrees. Or instead, you can use this concept that I was saying, that the tan of theta approximates to the sine of theta when theta is small. So you can use 1 over 20 as it is. Still, it's okay with this calculation. All right. So this is going to be our potential energy in this case, which is going to be 819,120, 712 joules. So take note, energy is measured in joules. So if you convert to kilojoules, divide by 1,000, this is going to be 819,121. So that will be 121 kilojoules. That is if you are to convert to kilojoules. Okay, so this information is very, very important. This is how we answer these typical questions. When we are given an incline, it's just a combination of formulas that you're supposed to work with, or that you're supposed to use in this case. All right, so let's check the other part of our question that is now on question 1.2. If you check on 1.2, we are now given a flat belt has a speed of 72 kilometers per hour. The tension of the tight side is 600, and the tension ratio. Okay, so let's just list the information that we're given. So we have given the speed of the belt in kilometers per hour. So this is the linear speed, which we can take as a V, which is supposed to be in meters per second. So that's 72 kilometers per hour. But know that in a meter per second, this is equal to 3,6 kilometers per hour. So you can divide by 3,6 to convert to meters per second. So this would be 20 meters per second. So that's our velocity. Then we are given the tension of the tight side. Remember our tight side, that's T1. So our T1 is given as 600 Newton. And we do not have T2, which is the slack side. So T1, this is our tight side. And T2, this is your slack side. All right, so we do not have this one. And we also have the ratio, that is the tension ratio, 4:1. That is the T1 to T2 is the same as 4:1. So remember, T1 to T2 is the same as T1 over T2. So this is equal the same 4/1. So this can be written as 4/1. So you can manipulate any formula from this ratio, okay? So the question on the first part was to calculate the tension in the slack side. 1 mark for that, 1.31. Okay, so how can we calculate the tension from the slack side in this case? Okay, so using the ratio that we have got here, we can calculate, or we can make T2 the subject, or we can just substitute our information, guys, as it is, because we know that T1 over T2 is equal to 4/1. So you can just substitute T1. We have got our tight side, which is 600. So this is going to be 600 over T2, which is equal to 4/1. So here we are going to have our ratio from this part. All right, so that is 4/1. So you can make T2 the subject by cross multiplying So if we cross multiply here, we can have T2 multiplied to 4. So this is going to be 4. T2 is equal to 1 times 600. So we are going to obtain 600 from there. To obtain T2, you can divide by 4 both sides since we are multiplying here. So you can remove this by multiplying. So by dividing, so that is 600 divided by 4, which is going to give us 150 Newton. Okay, so this is how we can obtain our T2 in this case, which is the slack side, okay? The force that we have or the tension that we have on the slack side. Okay, then on the other part on 1.3, 2 is to calculate the effective tensile force. Okay, so that is our TE, which is the difference between T1 and T2. All right, so 1.32, remember that effective tension is equal to T1 minus T2. So this is going to be the tight side minus the slack side. So the tight side, that is 600 minus the slack side, which is 150 Newtons. So you can have the effective tension 600 minus 150. This is going to give us 450 Newton in this case. All right. So remember that also the effective tension is the one that you use to calculate the power, which is the question that is following here. 1.32, the power transmitted, 2 marks for that. Okay. So remember that the power from the effective tension that we have, we can have our power in this case as the product of the effective tension times the velocity in meters per second. That is the most important part that you're supposed to have. Your velocity is supposed to be in meters per second. So already we've got our effective tension here, which is 450 times the velocity already we calculated. Remember, we converted to meters per second. We got 20 meters per second. So here we are going to multiply by 20. So that is our P is equal to 450 times 20. That is 9,000 watts. So we are going to have our power as 9,000 watts. Okay, of which you can convert this to kilowatts, divide by 1,000. So this will be 9 kilowatts. Okay, so this is how we can calculate power from the effective tension and the velocity. All right, let's check the other part of the question. 1.34. The velocity ratio if the diameter of the driver pulley is, okay, so here we are given the diameters. All right, so which means this information for now is not important. All right, so here we have got 1.34. We are asked to calculate the velocity ratio given the diameter of the driver pulley and the diameter of the driven pulley. Okay, so this is what we have taken note. This is in centimeters. So it's either you are going to convert this to centimeters or you convert this to meters. So this can easily be converted to centimeters multiplied by 100. So that is 12 centimeters for the driven pulley. Okay, so what is the formula actually for the velocity ratio when we are given diameters? So this is the diameter for the driven. Okay, so the diameter of the driven over the diameter of the driver. So this is going to be the diameter of the driven, all right, over the diameter of the driver. So that is how you are going to obtain your velocity ratio in this case. So meaning to say our velocity ratio, we've got the diameter of the driven part, that is the 12 centimeters, this one that we the one that we converted to centimeters. So it's going to be 12 over the diameter of the driver, the one that is drive, which is the 20 centimeters. So this can give us a ratio. If you reduce this as it's going to be 3/5. So remember, ratio can be a fraction or it can be written as 3:5 like this. Still, it's the same expression for the ratio. Okay, so this is what we had from this question, having a total of 16 marks. So these are the typical questions that actually you might be given as long you are working with motion, energy, and power. So we shall have more questions from Meson African Motives till we meet again.